Welcome to this comprehensive lecture on linear programming problem forms. Today, we are going to learn how to translate real-world optimization goals into the precise mathematical languages required by computer algorithms. Whether you are scheduling thousands of delivery trucks or managing a factory floor, understanding these mathematical forms is the very first step to finding the best possible solution. Let us begin our journey. Before we dive into the mathematical equations, let us understand why this concept matters and what we are trying to achieve. Imagine you are packing a suitcase for a flight with a strict weight limit, and you're trying to maximize the total value of what you bring. In mathematics, this is known as a linear programming problem. We have a main goal, called the objective function, and strict limits, called constraints. The term linear simply means that if we graph these relationships, they form straight lines or flat planes. To solve these problems using computers, we must organize them into specific structures. Now that we understand the basic idea of optimization, let us look at the most flexible way to write these problems, known as the general form. This form matters because it is how we naturally write a problem directly from a word description, before any mathematical manipulation. It simply lists the objective function first, followed by all the constraints. The constraints in this form can be a messy mix of less than or equal to, greater than or equal to, or even exact equations. It is the raw, unpolished version of our real-world problem. This brings us to the mathematical representation of our main goal. The objective function calculates our total profit or cost, and conceptually, it is just the sum of the individual profits from each item. The variable z represents this total value that we want to maximize or minimize, like total dollars of profit. The variables x1 and x2 are our decision variables, representing the unknown quantities we need to find. The symbols C1 and C2 are the profit coefficients, meaning the profit from exactly one unit. As you increase the decision variables, the total value z increases or decreases accordingly. After defining our main goal, we must define the mathematical limits we face. This inequality represents a single constraint, such as a strict limit on available wood in a factory. The symbol B1 represents the total amount of the resource available to us. The symbols A11 and A12 are the resource coefficients, which tell us exactly how much of that resource is consumed by producing one unit. Finally, we have the non-negativity constraint. This simply ensures our mathematical model makes sense in the real world, because you cannot manufacture a negative number of physical items. Moving on from the general form, we have the canonical form. This is a more organized version, often called the natural state of a problem. If you want to maximize profit, your resources naturally have an upper limit, so all constraints should be less than or equal to. If minimizing cost, you have minimum requirements, so constraints should be greater than or equal to. In canonical form, every constraint must face the exact same direction. If one faces the wrong way, we simply multiply the entire equation by -1 to flip the sign. While the canonical form is neat, computer algorithms require something even stricter. The standard form is the most important format because it is exactly what the simplex method requires. The simplex algorithm cannot understand inequalities. It only understands strict equations. To convert our inequalities into equations, we introduce new variables called slack and surplus variables. A slack variable fills the gap in a less than constraint, while a surplus variable removes the excess in a greater than constraint. To make this perfectly clear, let us look at how a slack variable works visually. In this diagram, the total height of the bar represents the maximum capacity of a resource, which is a fixed limit. The blue section is the resource we actually use. The green section on top is the slack variable, representing the leftover unused amount. By adding the used resource and the slack variable together, they perfectly equal the total capacity. This simple addition is what allows us to replace an inequality sign with an equal sign. Now that we understand the concept of slack variables, let us see this in action with a concrete example. We are given a simple maximization problem to solve. Our objective is to maximize the profit function z equals 3x1 plus 2x2. We are subject to a single constraint. The sum of the two items must be less than or equal to 4. Because this is a less than or equal to inequality, we clearly have unused capacity that we need to account for before a computer can process it. To turn this into an exact equation for the standard form, we add a slack variable, which we will call S1. The inequality sign is gone, replaced by an equal sign. The equation now states that the items produced plus the unused space perfectly equals the total capacity of 4. Our objective function remains unchanged. Finally, we state the non-negativity constraint, making sure to include our new slack variable, because you cannot have a negative amount of unused space. Let us look at a slightly more complex example involving mixed constraints. We are given a minimization problem with two different constraints. Our goal is to minimize a cost function. The first constraint is a minimum requirement that must be greater than or equal to 12. The second constraint is a maximum limit that must be less than or equal to 8. We must handle each of these constraints one by one, carefully applying our rules to convert the entire problem into the strict standard form. Starting with the first constraint, we analyze its direction. Because it is a greater than or equal to inequality, it means we have produced an excess amount above our minimum requirement. To bring the total perfectly down to the exact requirement of 12, we must subtract a surplus variable, which we will call S1. This subtraction mathematically removes the excess, allowing us to safely replace the inequality sign with an equal sign without changing the meaning of the problem. Next, we look at the second constraint in our problem. Because it is a less than or equal to inequality, it means we have unused capacity. We add a slack variable, S2, to fill this unused gap, bringing the total perfectly up to the exact limit of 8. Finally, we list all original variables, the surplus variable and the slack variable, stating that none of them can be negative. The conversion to standard form is now complete, and the physical meaning is that all resources are perfectly accounted for. Now that we have our problem perfectly formatted in standard form, we face a new practical challenge. When real-world problems get very large, writing out hundreds of variables and equations becomes completely exhausting. This is where the matrix form comes in to save us. It is a highly compact, shorthand way to write the standard form using the rules of linear algebra. Instead of writing every single variable and coefficient individually, we group them into organized grids of numbers called matrices and vectors. Let us see how this powerful shorthand works for the objective function. This single tiny equation replaces the entire long addition equation we saw earlier, no matter how many variables there are. The symbol C transpose is the transposed vector containing all of our profit coefficients, and X is the vector containing all of our decision variables. Multiplying these two vectors together gives the exact same total profit Z as the long equation. As the values in the X vector increase, the total profit scales accordingly in a very clean format. Next, we write all of our constraints in matrix form. This incredibly compact equation replaces all the individual constraint lines in our problem, bundling them into one clean statement. The large matrix A contains every single resource usage number from our factory, organizing how materials are consumed. The vector X contains our unknown decision variables, and the vector B contains the total available resources. By writing the problem in this specific way, computers can use advanced linear algebra algorithms to solve the optimization problem millions of times faster than a human ever could, making it the industry standard. Let us review the key takeaways from today's lecture. We learned that a linear programming problem can be written in several forms, depending on our needs. The general form is how we naturally write the problem from a word description. The canonical form organizes the inequalities to face the same direction. Finally, the standard form uses slack and surplus variables to convert all inequalities into exact equations, which is the absolute foundation required by computer algorithms like the simplex method. You now have the tools to translate any real-world optimization problem into a format a computer can solve.